I'm going to go over some problems from the chapter review at the end of chapter 7 in the book. These 6 problems right here, 4, 10, 11, 18, 26, and 28, are all from the chapter review, and then I've supplemented it with 2 of my own problems that I'll go over at the end. Our first problem here is evaluating a definite integral. We've been asked to integrate from 1 to e the square root of natural log of r divided by r dr. And the first thing I'm going to do is rewrite the integrand a little bit. I'm going to say this is the integral from 1 to e of the square root of the natural log of r times 1 over r dr. These are the same thing. Now, why do I want to do this? Well, what's the derivative of the natural log of r? It's 1 over r. So when I do my u substitution, I'm going to choose u to be the natural log of r, and that tells me that du will be 1 over r dr, which is what I have right here. So now I can rewrite this integral in terms of u. So I'll have the integral, and don't forget that these are x values right here, my limits of integration. So x goes from 1 to e. We have to figure out what u goes from. So start with 1, we'll plug it in. Oh, this is supposed to be r values, not x. We're using r. Same idea. R goes from 1 to e. So if r is 1, well, natural log of 1 is 0, so that tells me u starts at 0. And if r is e, I plug in e right here, natural log of e will be 1. So u will go to 1. So we have integral u going from 0 to 1 of natural log of r, which is my u, but I have the square root as well. So I'll have square root of u, and then the 1 over r dr right here, that is my du. And now we're ready to integrate this. We just have to rewrite this as a power function. So we have the integral u going from 0 to 1, u to the 1/2. Square root of u is like saying u to the 1/2 power, then du. And I'll go through all the steps to make sure it's clear. So when we have the power function that we're trying to integrate, we first add 1 to the power. So we have 1/2 plus 1 is going to give us 3/2. Then we divide by the new power. So dividing by 3/2 is like multiplying by 2/3. And we found an antiderivative for u to the 1/2. So now all we have to do is evaluate this from 0 to 1. And because the 2/3 is a constant multiple, I can put it on the outside and put parentheses like this. So we'll say that this is equal to 2/3 times 1 to the 3/2 power minus 0 to the 3/2 power. 1 to the 3/2 power is 1. 0 to the 3/2 power is 0. 1 minus 0 is 1. Multiplying by 1 doesn't change anything, so this factor cancels itself out. And all we're left with is 2/3, and this is the solution to the integral. And if you'd like to put that in the calculator to check, you can. Next problem, we have another definite integral. And I see my x squared right here, and the 2x right here. So that suggests me to put u equal to the denominator. So I'll do this. U equals x squared minus 3x. And du will be, well, derivative of x squared, it will be 2x. And derivative of minus 3x will be minus 3. And then we'll have the dx out here. And we have to write this with u values. So if x is going from 1 to 2, I'll plug 1 into these x's here. 1 squared is 1. Minus 3 times 1 is 3. Is minus 2. So u starts at minus 2. And then I'll have to go ahead and also plug in 2. I have to take this 2, the upper limit, and plug it in for the x values here. So 2 squared is 4. Minus 3 times 2 is 6. That'll also give me negative 2. So now, my integrand, I don't care what the heck it is, because I'm going from negative 2 to 2. So I know that it's just going to give me 0 because there is no area at one point. And as it happens, I don't know a way to integrate this too well. Maybe non-elementary, or you may need partial fractions, which is a BC topic, or integration by parts. But if we just have the integral from -2 to 2, we know that it's going to be 0. And now we have a couple of indefinite integrals. So this time we're looking for all the antiderivatives of the integrand. Now I have sine of x on the bottom, cosine x on the top. I know that the derivative of sine of x is cosine of x. So that suggests me to take my u to be sine of x, and my du will be cosine x dx. We have that right here. So this is going to be the integral of, I'll put a 1 on the top, 1 over 2 minus sine of x is my u, and then this cosine x dx right here is my du. And now I can integrate this. I have a linear function in the denominator, so my answer is going to be natural log, absolute value of that linear function. But then here's where we have to kind of do the chain rule in reverse. Think about taking the derivative of this. You do 1 over the inside of the natural log. Then you have to multiply by the derivative in here. In fact, I don't need to put down absolute value again when we're doing the derivative, because it could be positive or negative. But I'd have to multiply by the derivative of this, which would be -1 because of the chain rule. So I have to do the division here. I have to divide by the derivative in here. The derivative in there is -1. Dividing by -1 is the same as multiplying by -1. So I have to put down negative in the front. And because we have to find all the antiderivatives, I have to add an arbitrary constant. And now we have to put the u back as x. So we have negative natural log absolute value of 2 minus sine of x plus a constant. Now if you like, you can put this down for your answer, and it will be correct. But if they give this to you on a multiple choice question, they'll probably play with you a little bit. They'll probably take this negative. The -1 coefficient of the natural log becomes the exponent for the inside of the natural log. That's one of the properties of logarithms. So we will have natural log, absolute value, 2 minus sine of x, raised to the negative first power. Again, I just took this -1 from the front and made it the exponent for the inside by the log property. Now, when you have something raised to the -1 power, that's like saying the reciprocal of that. So I can write this as negative, or well, not negative anymore, just natural log of 1 over absolute value of 2 minus sine of x. And there's a constant here and a constant here. So you could put down any of these three. Any of these three. These are all just different expressions, different ways of expressing the same expression. So these are all correct. And then we have one more indefinite integral, I believe. Now, I don't like it when they put the dt in the numerator like that. I like to have it at the end, so I'm going to rewrite this as 1 over t radical t dt at the end like that. Now, this might look scary, but in reality, this is just a simple power function. So we have the integral of 1 over t is like saying t to the first power. I'll just leave it 1 like that. Plus square root of, well, not plus actually, it's times. Let me write this a little neater. Square root of t is like saying t to the 1/2 power. Then we have the dt. So on the bottom we have a product of two powers with the same base, so I can just add the exponent. That's the kind of stuff you learn in elementary school. So we have the integral of 1 over t to the 1 plus 1/2 is like t to the 3/2 dt. And when we have 1 over t to the 3/2, that's like saying integral of t to the negative 3/2 power dt. And now I have a nice simple power function that I can integrate. So this is going to be t. I'm going to add 1 to the power. So negative 3/2 plus 1 is going to give me negative 1/2. Then I have to divide by the new power. Dividing by negative 1/2 is like multiplying by negative 2. And here's an antiderivative, so if I put plus c, I'll have found all the antiderivatives. And this is our solution to the integral. Now we have a few initial value problems and then one slope field problem that I'm going to still go over. Now, in the directions, it also asks you to overlay the graph on the slope field. Now, I don't have a nice, easy way to do that on my screen, and it's also highly unlikely that they're going to ask you that on the test, so I'm going to leave that part to you. So we've been given this differential equation. We have to solve for y in terms of x, given this initial condition right here. And the first thing I'm going to do is rewrite this as a point, because I like points. Y of 1 equals 1, that means this graph goes through the point 1, 1. Now, first thing, separate variables. This dx needs to come on this side. So I'm going to multiply both sides by dx. I'm going to do dx times this side and dx times this side. On the left-hand side, dx's cancel out. I'm left with dy. And on the right-hand side, I have x plus 1 over x quantity squared dx. Now that I have dy on the left and dx on the right, I can integrate both sides. So integrate. Left-hand side, integral of dy is y plus a constant, which I'm going to call c1, equals, well, to integrate this, I have to go ahead and expand this square. So I know that when I'm squaring a binomial, I'll get square of the first term plus twice the product of the terms, so I'll have 2 times x times 1 over x, plus the square of the second term, which will be 1 over x squared. And then I still have the dx right here. So now I can integrate this. But before I do that, I'm going to make a little simplification. X times 1 over x cancel out. So this is going to be equal to, so we're integrating x squared. So you add 1 to the power, you get x cubed, then divide by the new power. Integrating 2, you'll get 2x. And the 1 over x squared right here, I'm going to rewrite, whoops, it's supposed to be an eraser. I'm going to rewrite this as x to the negative 2 power. So this is going to be x to the negative 2. I'm going to add 1 to the power, so we'll get x to the negative 1 power, then divide by the new power. Dividing by negative 1 is the same as multiplying by negative 1, so I'll just put down a negative in the front. And then here I have to add another constant. Okay, I'm going to put the constants together. I'm going to subtract c1 from both sides. I'm going to subtract c1, subtract c1. That tells me that y equals x cubed over 3 plus 2x minus x to the negative 1. I can rewrite that as 1 over x. Doesn't really matter. c2 minus c1. Well, if you have a constant and you subtract another constant, you're going to have another constant. So I'm just going to call that new constant c. Now we solve for y in terms of x, but we have this c here that we have to solve for given this right here. We know that this graph goes through the point 1, 1. So what I have to do is put the point 1, 1 into my y and x values here to solve for c. So doing that, I'll have 1 equals 1 cubed is 1 over 3, plus 2 times 1 is 2, minus 1 over x is 1, 1 over 1 is 1, plus c. 2 minus 1 is 1, and that's going to cancel with this one right here. These cancel out. So I'm left with 0 equals 1/3 plus c, which tells me that c equals negative 1/3. So now all I have to do is put that in right here, and I'll rewrite the whole thing, because they'll want you to do that on the test. So now we know that y equals x cubed over 3 plus 2x minus 1 over x minus 1/3. And now we have solved for y in terms of x, and we're done with this problem. I'll do a couple more of these. Next one, we have some trig functions here. So this will also give us some practice with integrating trig functions. First thing I'm going to do is put down some parentheses here so we don't get confused. I wish they would do that in the problem. And I'm going to rewrite this as the point pi over 4, comma 1. All right, again, separation of variables. Let me move this over a little bit so I have some room. I'm going to multiply both sides by d theta. So I have d theta times this side and d theta times this side. Again, on the left, the d thetas cancel out. I have dy, and this will be equal to cosecant of 2 theta, cotangent of 2 theta, d theta. And now I have dy on the left, d theta on the right. I can integrate both sides. So I'll do that. I'll say integrate, and integral of dy, as we know, is going to be y plus c1. Now here's where we have to be careful. I'm going to leave a little more room here. You'll see why in a second. So we'll say we have cosecant of 2 theta right here, and integral sign right there. Let's take a side note here. Derivative of cosecant of 2 theta, well, that's going to give me negative cosecant of, let me do this on the next line so I don't run out of room. It's going to give me negative cosecant of 2 theta, cotangent of 2 theta, but then the chain rule I have to multiply by the derivative in here, which is 2. So if I put down a negative 2 right here, then the antiderivative for this right here will be cosecant of 2 theta. Of course, I can't just put down negative 2. That changes the value of the whole thing. But I can fix that by multiplying by a negative 1/2 in the front. So now I haven't changed the value of anything, because negative 1/2 times negative 2 is 1, and those cancel out. So now on the right-hand side, I can conclude that this is negative 1/2 times, let me just erase this down here so I have more room. The integral of negative 2 cosecant 2 theta, cotangent 2 theta, d theta, that's what we just proved to be cosecant of 2 theta plus another constant. All right, once again, I'm going to put the constants together. I'm going to subtract c1 from both sides. I'm going to say y equals negative 1/2 times the cosecant. I don't even need these parentheses right here. Times the cosecant of 2 theta plus c. Now I just have to use my initial condition right here, pi over 4, 1. So I'm going to plug in 1 for all my y's and pi over 4 for all my thetas. So I know that 1 equals, well, let me get some more room here first. I know that 1 equals negative 1/2 cosecant of 2 theta, which is pi over 4, plus a constant, and 2 times pi over 4, that's going to give me a pi over 2 in here. Cosecant of pi over 2, well, cosecant is the reciprocal of sine, and the sine of pi over 2 is 1, and the reciprocal of 1 is 1. So we can conclude that the cosecant of pi over 2 is 1, so I can cancel this factor out, and I'll just have the negative 1/2 in the front, because multiplying by 1 doesn't change anything. So I'll say that 1 equals negative 1/2 plus c. Add 1/2 to both sides, c equals 3/2. So now all I have to do is plug that back in right here. So I'll rewrite this. Y equals negative 1/2 cosecant of 2 theta plus 3/2. Now I have one more initial value problem. This time we have to deal with both variables. This time we have both variables on this side. So when I'm separating variables, I have to make sure I have all my y's on one side with the dy, and all my x's on the other side with the dx. So, actually I don't have to move it. I'm just going to say that dy dx equals, I'm going to factor out an x from both terms on the right-hand side. So x into x goes 1, x into xy goes y. And now I'm going to do my separation of variables. I'm going to multiply both sides by dx over 1 minus y. You'll see why in a second. Times dx over 1 minus y. This way, on the left-hand side, the dx's cancel. On the right-hand side, the 1 minus y's cancel. So I'm left with dy over 1 minus y, which I'm going to write like this. 1 over 1 minus y equals, and on the right I'm left with, I put dy equals x dx. So now I have all my y's on the left with the dy, all my x's on the right with the dx. I can integrate both sides. So integrate. And let's also take a note of this condition before I get rid of it. This is the point 2, 0. So integral of 1 over 1 minus y is going to be natural log absolute value of 1 minus y, but then the reverse chain rule says I have to divide by the derivative in here. So I have to multiply by negative 1 again. And then I'll have, I'm not even going to put down plus c, 1 on the left-hand side. I'm just going to put down a plus c on the right. It'll just save me the step of combining the constants. Equals integral of x is x squared over 2, and then I'll put down just 1 plus c on the right. Then I have my initial condition to 0. So I'm going to plug in 0 right here and 2 right here, so I'll have negative natural log of absolute, well, I don't need absolute value because 1 minus 0 is 1, so I'm just going to have natural log absolute value of 1, which absolute value of 1 is just 1. Equals x squared over 2, x is 2, 2 squared is 4, 4 over 2 is 2, plus c. Natural log of 1 is 0. Negative 0 is still 0, so I have 0 equals 2 plus c. C equals negative 2. I'll plug that in here. Negative natural log absolute value of 1 minus y equals x squared over 2 minus 2. Are we done yet? Might seem like it, but no, we have to solve for y in terms of x. This is an expression in terms of y, but it's not just y. So we have to do more work. First thing I'm going to do is bring the negative on the other side. I'm going to multiply both sides by negative 1. Gives me natural log absolute value of 1 minus y equals negative x squared over 2 plus 2. Now to get rid of the natural log, I'm going to do e to this power and e to that power. And that tells me that e to the natural, well, I don't need to write it like that because e natural log cancel out because those are the inverse functions of each other. So we just have absolute value of 1 minus y equals e to the negative x squared over 2 plus 2. Now I just have to do the two cases here because I have the absolute value. My two cases are going to be when y is greater, or when y is less than 1, or when y is greater than or equal to 1. If y is less than 1, this will be positive, so I don't have to worry about the absolute value. And if y is greater than or equal to 1, then this will be negative, so I'll just have to take the opposite of it. So we'll do this one first. So we'll say if y is greater than 1, then I don't need the absolute value. It's just going to be 1 minus y equals e to the negative x squared over 2 plus 2. And then I will, let me just leave this on the screen. I will subtract 1 from both sides, and I will get negative y equals e to the negative x squared over 2 plus 2. and then minus 1 down here. Don't put your minus 1 up in the exponent. You'll get the question wrong. And then I'll just multiply both sides by negative 1, and I'll get y equals negative e to the negative x squared over 2 plus 2 plus 1. And this is our solution for if y is greater than 1, or rather if y is less than 1. So this is part of our solution. Now I have to deal with this case. So let me just firstly recopy the equation. Absolute value of 1 minus y equals e to the negative x squared over 2 plus 2. Now we're considering what's going to happen if y is greater than or equal to 1. Well, my inside here is going to be negative, so when I take the absolute value, I have to take the opposite of it. So absolute value of 1 minus y is going to become y minus 1, because it's going to be negative, equals e to the negative x squared over 2 plus 2. And I'll add 1 to both sides, and I'll get y equals e to the negative x squared over 2 plus 2 plus 1. So this is for if y is greater than or equal to 1. So this is the second part of my answer. So these two statements form the answer to our initial value problem. Okay, last problem. Slope field. Sometimes they'll give you a slope field and you'll have to match it to an equation, or sometimes they'll ask you to draw a slope field. I'm going to draw a slope field. You'll probably have to draw it on a lattice grid like this. Now, dy dx, remember this. This is the slope. That's where people get confused. Even I've gotten confused on that sometimes. So what we're going to do is take each of these 12 points that they gave us, and we're going to plug in the x and y values right here and see what the slope is, and then we're going to draw a little short line with that slope over that point. So we'll start with the point here, 0, 0. So when I plug in 0, 0 right here, x cubed times y, well, 0 cubed times 0 is certainly 0 over, doesn't matter, slope there is 0. So I know that my slope at this point is going to be 0. So let me see, I'm going to try to draw a horizontal line there with slope 0. It's kind of hard to draw on the screen. On the AP test, usually they give you 1 point for the 0 slopes and maybe another point for all the other slopes. All right, let's pick another point. Let's do this one. So this is the point 1, 0. So I'm going to have 1 cubed times 0 is 0 over 1 minus 1. Oh, sorry. Yeah, this is the point 0, 1. So I have 0 cubed times 1 is 0 over 1 minus 1 is also 0. Undefined. No dividing by 0, so there is no slope here. So wherever y equals 1, I'm going to have a 0 in the denominator. So for these 3 points, there will be no slope. Don't put anything down there. Now another thing is to notice that wherever x or y is 0, except for at y equals 1, my slope will be 0 because I have a 0 in the numerator. So wherever x or y is 0, I'm just going to put down 0 slopes. So I'll have a 0 slope here, 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 here. Well, not there because that's where it's undefined, and here. So those are my 0 slopes. Now I only have a few points left. So over here, for example, at 1, 1, well, my numerator is going to be 1 cubed times 1 is 1. Sorry, this is 1, negative 1, over 1 minus negative 1, which is 2. So my slope there is 1/2. So a slope of 1/2 is going to look something like this. Closer to horizontal than vertical. And then I'll do this point. Right here is going to be negative 1, negative 1. So in the numerator, I'll have negative 1 cubed is negative 1 times negative 1. It's going to give me positive 1 over 1 minus negative 1. It's going to give me 2. So my slope there is also going to be 1/2. And remember, I don't have to do either of these points because they're not defined there. So I just have to do this point still and this point. So this point is -1, -2, -1, 2. So put in -1 cubed, I get -1 times 2 gives me -2 over 1 minus 2 is -1. So -2 over -1, my slope is going to be +2. So I'll try to draw a slope of +2. At this point, it's going to be kind of upward like that. Mine looks kind of vertical. Yours shouldn't be quite so vertical. And I just have one point left. This one right here is my point 1, 2. So I have 1 cubed times 2. It's going to give me 2 over 1 minus 2 is going to give me -1. So my slope for this one is going to be -2. So it's going to look something like that. And that is our slope field.